So, welcome to Service Mesh Academy. Oh, good. The music did cut off. I'm really glad that happened. Um, I'm Flynn. I'm a tech evangelist for Buoyant. I'm joined today by Bailey Hayes, the Chief Technology Officer for Cosmotic. She has a much more impressive title than I do. It's really kind of sad. We're kind of continuing our trend for Service Mesh Academy in 2025 of trying to go through, grab some technologies that people may not be familiar with, and sort of do the 101 bit with them and show a little bit about how they can interact with Linkerd as well. So today we are going to be talking about Wasm, WebAssembly, with Linkerd. If you want to follow along, well, actually, you know what? I'm getting ahead of myself already. We're going to do an intro to WebAssembly. We're going to do an intro to wasmCloud. We're going to do a very quick intro to Linkerd. And we're going to talk throughout about why you should care about this stuff. We're going to do some demos. We're going to end up talking about gotchas as always. If you want to follow along at home, there is the source code. The QR code there will take you to that repo. Sorry, this is the point where I'm looking over going, you know what? I need to fix that slide, don't I? So let me just go ahead and do that while we're all watching me screw around with stuff that should have been working originally. Right. Just pretend you didn't see anything off about the last couple of slides. I appreciate that. I'm going to be using Buoyant Enterprise for Linkerd 2.18, specifically 2.18.1, but any Linkerd Edge 25.4.4 or later will work. I will also be using K3D, but the cluster type you're using really, truly does not matter. We do need a load balancer in there, but that's about it. Okay. You will need kube control, the Linkerd CLI, Helm, ideally BAT and JQ. So yeah, there we go. All right. Also, that's the URL if anybody particularly wants it. So over to Bailey. Bailey, what is Wasm? What are we talking about here?
Yeah. What is Wasm indeed? Well, you already slipped up. You already called it WebAssembly at one point, so we should probably just explain that a little bit. So Wasm's short for WebAssembly. And now we're talking about Linkerd, and then you hear the word web in here, and that kind of sounds weird. So let's dive in a little bit more on what we mean by that. So WebAssembly itself, it's a portable compilation target that many languages support. On the left-hand side here, I show basically the command that you would run to be able to produce a .wasm. And once you have that .wasm, you're able to run it basically in any WebAssembly runtime. That could be your browser. All the browsers that you're using today, they have it, but also a ton of other things that you probably don't realize, like Netflix, Disney+, Zoom. You're using WebAssembly all day, every day. You don't even know it, and you can also use it on your cloud. So that's obviously the side that we're going to be speaking to. But once you have it, you take your .wasm, you run it in a WebAssembly runtime. It's the WebAssembly runtime's job to then compile that down into machine code to make it work for your architecture. So why Wasm? Why would you want to do this? Well, I already called out its portability side of it. That's a pretty big win. You compile all of your code once and run it everywhere. We might have heard that before, but we mean it for real this time. Wasm itself, the reason why it's so cool for the server side is that it solves the cold start problem. It starts in microseconds, which means you really, really do scale it all the way down to 0. And then when you need to run a workload against it, you scale it back up. And it'll start in microseconds, basically, instantly. The size is also incredibly small. That's one of the key reasons why it's super awesome for the web, but also a good reason why it's awesome for the cloud. So you're usually measuring a .wasm in kilobytes and not megabytes or gigabytes, which is a little bit more common for containers. And something that's really important to call out that a lot of people don't talk about on the Wasm side, but is actually a huge feature, which is Wasm apps are sandboxed, and they have a capability-based security model, which means you give it permissions, you give it effectively a function handle that it's allowed to call, the thing that lets it do networking, for example, and the Wasm app itself will call that, and that's what gives it that capability. So we'll dive in a little bit more on that in future slides. But there's also a key difference that I want to call out. We're talking about WebAssembly components, Wasm components, and not Wasm modules. And so in the world that we're building with composable Wasm components. So we can take a component written in Rust, a component written in Go, compose them together. Different, component A is a .wasm, component B is a .wasm, and compose them together. And those two different components are able to communicate with each other. But the way that we do this is via still maintaining a fine-grained sandbox so that the component A and component B actually still have their own tables and memories. And the only way that they're able to communicate once you compose them together is over those interfaces. And the way that we define those interfaces is with an IDL called WIT. That's the WebAssembly Interface Type. That's one way to define your interfaces. If you're, feeling brazen or you do some assembly programming like I do, there's also a way to define the component itself with something called the WebAssembly textual format, which is just basically writing it in the binary itself. Is another way you could do that, but mere mortals mostly use WIT, and that's usually done by your language toolchain.
I'm sure there's nothing to be read into the fact that the WebAssembly text format abbreviates to WTF.
It's actually WAT, like,
right. What I was going to say here is one of the interesting things about this particular slide that I wanted to call out is later on we'll be talking about how we use some of this in the demo, and it's fascinating to me to realize that there is more than one component in that thing, and I have no idea what one of them is implemented in at all. It doesn't matter. It's kind of cool. Yeah. Yeah, that's pretty cool.
Yeah, and so because of that means that you can write whatever you need to with whatever language or tool is best for the problem that you're trying to solve, and you're able to work with other teams. And so there are these new patterns basically that are emerging right now in this space. I call them micro monoliths, but it's where basically people are taking what were microservices and then composing those together and then deploying them together, because for the most part they had the same scaling properties. They were really chatty, basically best friends with each other. And instead of trying to refactor their apps to become, old school monolith, they're able to build them with WebAssembly components. And that's super powerful. One other thing I want to call out, though, when you compose these components together, it makes a new .wasm, which means when it's loaded up by a WebAssembly runtime, it's actually all the same process, which means these two components are able to talk to each other in nanoseconds, because again, same process, but done in a way where each one of them has their own sandbox. It's pretty cool.
Surreal, but pretty cool.
Pretty cool. All right, so that's
I think that takes us up to wasmCloud, right?
Yeah, now we're moving into the good stuff. So you've got a new unit of compute. Now you need to orchestrate it. So, just like how Kubernetes orchestrates containers, wasmCloud's job, which is a CNCF incubating project, is to do Wasm native orchestration. And wasmCloud itself is designed to be able to let you do this from basically any device, edge, server, or cloud, including your own. Now, when we look at the landscape of the world, what we're seeing is people are kind of moving along on top of Kubernetes itself. And so they're deploying wasmCloud very frequently on top of Kubernetes. But what I want to highlight is that when we look at platforms as they've evolved over time, notice that the level of abstraction just keeps getting raised. When we were doing just bare metal and we built out virtual machines, we virtualized the hypervisor. With containers in Kubernetes, we basically virtualized effectively the operating system that we're building with, and then also the kernel that we're running on top of. But inside that container, we're still shipping along basically POSIX plus our application plus all of our libraries. And when we go to WebAssembly applications, those WASM apps, you're literally just moving around your code. And Flynn, I think you're going to highlight this a little bit more in the demo, where you had this aha moment where you're like, wait, that's not even in there. And that's not even in there. It's going to apply to a ton of different things when you talk about what's built into the WASM binary. And so, we're trying to call this the componentization era.
Ooh, yeah, I'm definitely going to talk a little bit about that. I think the right way to phrase some of that was, it's very easy to write container code without thinking about what all has to come along in the container for it to work. And it was also pretty easy to write and work with the WebAssembly component will be showing without thinking about what didn't have to come along with it. But it was, yeah, we'll talk a little bit more about that because it's really kind of cool.
Yeah. Now, so I'm not to bash on containers because containers are awesome. With every,
right.
epic of computing, the previous one didn't go away, right? It never does. You find a way to work with it and take advantage of what it's great at. And, with the new tech, you figure out how to make that new tech sing. So, what Wasm's kind of solving for you, why you should be interested in it for your microservices, is that you might be experiencing some of these problems with containers, which is they default to being wide open. So a lot of the work that we do today in our current infrastructure is to find ways to lock them down and basically take things away from it. They also suffer from cold starts. So right now, today, we have a ton of idle infrastructure because it takes seconds to start containers, which means even if you have a really advanced platform and it's trying to scale everything down, it never actually scales it all the way down to zero because you don't want to deal with a really long cold start when somebody calls you later on. So we have a lot of containers that are just kind of hanging out. And those containers themselves, they're bloated. They're bringing along a lot that's in it. They're typically going to be hundreds of megabytes. If something really strange is off, maybe they're gigabytes. But that's partially because when you build it, you're building in everything, right? Everything that your application possibly needs to run. Whereas with a Wasm app, it really heavily relies on what's provided by the WebAssembly runtime. So that piece isn't shipped along inside that app. It gives you this really secret kind of advantage in that because you're not shipping that around, you're not locking yourself in into having to manage all these different types of dependencies for all the different clients of all the different things that you're trying to connect to when you're running your app. And what that effectively means is that you can avoid a lot of the different types of problems that people run into today with containers where they have to, if a vulnerability happens for, let's say the driver that they're using to connect to Postgres, that may now have to be patched in hundreds of different applications because everybody in your platform has the exact same golden template that you're following. So you have to do this kind of application by application maintenance. Whereas with Wasm, that's something that we're able to patch with wasmCloud at runtime, which is pretty powerful. So that's one of the things I want to recommend taking advantage of. Yeah, Flynn?
So let me ask the loaded question here. How often do you have to deal with one of these interfaces deciding to break a contract because of some security bug with the Postgres driver or whatever? Because it seems like there's still going to be at least the potential for places where a fix happens, the interface breaks, you now have to go through and recompile the world, even for no particularly good reason. So how, in practice, what does that look like?
Yeah, I think it really depends on how you define your interfaces. And it's very much a choose your own adventure right now, which is good and bad. The choose your own adventure that I've been seeing, and actually there's a really great talk that American Express gave on their use of wasmCloud. And effectively they use this pattern called the platform harness pattern, where they create a component that has all that stuff in it. It has all those interfaces. And then they're basically building a FAS type platform on top of that, where their component just has a handler. And so the code to actually talk to the databases, to talk to key value, to talk to messaging, all of that is actually handled inside that platform harness. The frequency at which this needs to change, I think the platform harness itself needs to rev about every week. It's sort of in highly regulated environments, right? You're under contractual obligations to fix any high CVE in a really short time period. And so the platform harness component is the thing that's churning, and not what their developers who are building on top of their platform having to experience that. And so the reason why it's really valuable that they're able to choose their own experience here is that they've created an interface that's super simple. It's like invoke. That is literally the interface that they're supporting for their developers, and they've bound and own all the other ones. And so in terms of like how often are those contracts breaking, it's like super rare. How often are the dependencies that are bundled inside that platform harness changing? Every week,
all the time.
Yeah, basically all the time. And so that churn happens in one place, one component that has to get reshipped and not everything else that's on top of it.
It would be really nice if we as an industry came up with a really, really good way to deal with problems like that. It hasn't happened in the last few decades, unfortunately.
We'll keep trying.
So all you people who are just getting into computing, there you go. There's your master's, actually your PhD thesis right there.
Yeah, love it. So
this actually, I didn't look ahead at the slide because we're kind of talking about this already.
Yeah, no, it's good. It was a perfect setup, right? So, hey, what do those interfaces look like when you're composing these components together? I'm calling out a couple of them. There are these WASI messaging, WASI key values. So these are like really generic kind of interfaces. Notice that it's not tied to, DynamoDB or to NAT specifically. These are intended to be, something that solves the 80% case. But if you want something that is specific to the type of thing that you're working with, which honestly, I see a lot of people falling in that category, we also have specific interfaces for that. And you can write your own, which is probably one of the most common reasons why people choose to use wasmCloud is that they're able to build out their own custom capabilities.
Do you always have to pick a specific provider, or like does wasmCloud give you a default messaging thing, or do you end up having to say at some point?
So we've gone, honestly, the maintainers in wasmCloud, we've gone back and forth on this because we want you to do capability-driven security. Like we want to be secured by default. And part of that is like opting into what capability you want to use. So people who build with wasmCloud, aka platform engineering teams that are creating a platform with wasmCloud, what they do is they create the platform defaults, and their developers don't worry about that. Like they don't even have these capabilities in theirs other than, hey, I need key value, I need Postgres. They build their component with that, and then when they get deployed on the platform, they just get linked up to whatever that platform provides.
That's a little bit of a cheating question because I'm also thinking over the Wasm service, that Wasm component that I was working with, and going, I don't think I remember ever asking for anything in particular, although it uses key value, for example. So somewhere somebody picked it.
It might have been me, Flynn. It might have been me. I put things in your WADAM. We should explain what a WADAM YAML is and what that CRD is. Yeah,
we can do that. We actually will do that as we go through the demo.
Yeah, we'll get through the code.
But this is also a great opportunity for you to define WASI now that you've mentioned it once or twice.
Yeah. And I'm sorry, since you're the slide driver, Flynn, this one's going to take a lot of clicks. So
man.
Here we go. All right. So WASI, the WebAssembly Systems Interface. It started in 2019, but Click, really, you should think about it as the WebAssembly standard interfaces. But when you create a WebAssembly module, and remember I was talking about components earlier. So in 2019, the world looked a lot like this. It was a monolithic ABI, and this is the WAT, W-A-T. Maybe we should have used WTF. I don't know.
I'm going to be calling it WTF until the day I die,
I mean, you could be like, what? What is this? Instead of WTF, it's kind of similar in a way. But yeah, this is the WAT here. So the first set of bytes tells you that it's a module. And it had some things in it that are kind of POSIXy, like giving you file system, IO, random, and clock. But notice that that's probably not good enough if you're trying to run a cloud application, because it's suspiciously missing something that most cloud apps have. It's called networking. So if we go on to the next slide.
Details.
Just some details there. Great for writing CLI apps, and actually WASI P1, what we just talked about, that's in millions of devices today. So wildly successful given even just that small set of constraints. And we learned a lot. So that went out in 2019. We've iterated quite a bit on that. I was fortunate enough to be the WebAssembly WASI chair at this time in January. So I held the vote January 2024. So we're past a year on this now. But effectively, we changed it to build on top of this new proposal called the component model. So that's why that first set of bytes, when you load up a WebAssembly component, it looks a little bit different. So this WAT gives us a lot more information about the interfaces that we're using, and that allowed us to change away from having a modular ABI, which a a monolithic ABI, which, as you can imagine, is kind of hard to update and manage. So just the problem of how do we give them networking now was actually pretty big challenge to figure out. So, hey, breaking it up into modular interfaces and adding things like sockets and HTTP is what we got out of WASI P2. And so that gives us new networking interfaces. And over the past year, many different languages, and I included those commands at the very beginning of this, now have this new target, Wasm 32, WASI P2. When you compile with that, like say if you compile with Clang, you say Clang -- target Wasm 32, WASI P2, out will come a component. Oh, no, this is good. Let's go into it. Okay. So, all right, that's enough on like standard stuff. When we actually look at, hey, what is the WebAssembly component? And one view of this, what we're looking at here is a component running inside a wasmCloud. So a component itself is running inside that WebAssembly sandbox. And this view is WIT, the WebAssembly interface type. So this is the IDL version of defining your interfaces. And so notice that when we load up a component, we get these interfaces fulfilled on our imports. And when you see an import, just think of it as a dependency. And a lot of those dependencies are fulfilled and managed by our WebAssembly runtime itself. Our WebAssembly runtime of choice is Wasm time. So if you click here, I'm going to give you some helpful little arrows so that you can see what links up to what.
Before we do that, I was going to jump in and point out one thing that I don't think we've talked explicitly about, which is that you can write components in a variety of different high-level languages that then get compiled into Wasm. So, like, I will confess, I have not yet had to mess with a WIT, and this is fine with me, right?
That's great.
So there are a lot of situations where you are going to be interacting with this system by writing a high-level language and just following some conventions for, you know, function names and things like that, which is another thing that's really nice about this. But knowing how it works under the hood is always useful. So let's see.
Hopeful arrows. I'm an under the hood kind of gal, but sometimes you're gonna have to create this, especially if you're on the platform engineering side of the world. You know, you might have your own custom interfaces and saying like, this is the contract my developers need to follow and adhere to.
Yeah. And it's very much worth pointing out that so far I have not written a component intended for other people to use as a dependency. Right. Although I was looking at the code earlier, I have not published the source code yet for the Wasm component we're working with, because frankly, it's in a state that kind of embarrasses me right now. And one of the things I'm thinking about doing as I clean it up is I'm kind of thinking maybe I should actually split that into multiple components, because because there are ways it would make sense in the context of the larger demo as a whole. So I may very well be candidly asking Bailey lots of questions about how this works later.
And if you do, I will point you at one of the examples that we have for Cosmonic, and it's called Cosmonic Labs WasmPay, and that'll show you how to use that platform harness pattern I've been talking about. But so if we take your component and we print out what its WIT is, it's going to look a lot like this one with a few less things. And such a good call out, though, that, you know, as a developer, no, you don't really need to deal with this. As a platform engineer, maybe you should be considering this part of the world. But as a developer, this stuff here is designed to be done for machines by machines. So that's why it just worked for you when you're compiling with Rust. And now that gets wired up with Wasm time. And then we can also fulfill capabilities that are external to the host, which are effectively plugins to our host, which we call capability providers. And in this example, we're giving it access to Postgres via wasmCloud Postgres interface. Now, one other thing that I'm going to call out on the next slide, if you go to it, is that you can also wire things up via these interfaces as if it was another component. Now, in this case, we're giving it to native code. That's what these capability drivers are things that maybe can't compile to Wasm, or you need to be taking advantage of hardware level optimizations that don't really make sense compiling into a WebAssembly sandbox. And so when you need to do that, you wire everything together still in this kind of component-y way, aka over interfaces that are strictly defined and versioned. So in this case, we're highlighting that it's coming from a provider, but we could also do this with another component, as you called out, and that's basically what a lot of people are doing, is building it out with components fulfilling other components, exports and imports. Okay, all right, let's go back up. Let's go out of the weeds and back to the high level. If you're running with CNCF wasmCloud, you can run it in Kubernetes. You can also run it on edges and lots of different types of devices. The WebAssembly runtime that wasmCloud is built around is called WasmTime. That's hosted inside the Bytecode Alliance, which is also another software foundation for building secure WebAssembly software SDKs. So a lot of the things that we're using to even compile our code to Wasm, that's also inside the Bytecode Alliance. But essentially, this is sort of our view of the world. For wasmCloud, we want to try to span the gamut, and that's why we're really well aligned with doing things with Linkerd. But what we're doing in this demo is talking about Kubernetes. So I'm just going to give you a couple little pointers on what we're doing with wasmCloud and how wasmCloud integrates with Kubernetes. So on the next slide, we talk a little bit about our wasmCloud operator. And inside our operator, we have some custom resource definitions that we define. We have basically our deployment manager. I don't know if you've caught on it yet, but basically everything in the WebAssembly ecosystem usually starts with WA, W-A. So in this case, our deployment manager is called WDAM, kind of like a punch. So WDAM, you've got your application manifest. It's built on the Open Application Manifest spec. And that gives you, some of your integration points for services and how we wire together these imports and exports. The other custom resource that you use in your demo to do this deployment is our wasmCloud host definition. So that's the wasmCloud host config. And that is where we deploy our components. So components go and run on a WebAssembly host. And that's defined a little bit more on the next slide. And what that basically
how many components can you have in a wasmCloud host?
Well, how big is your host? So if you have, let's say, okay, yeah, well, on my MacBook, I have, I think, 32 gigs of RAM, and on a single wasmCloud host, I've been able to get easily up to 10,000 unique WebAssembly components, which is crazy.
Which is cool.
It's so cool. And there's a lot of companies, a lot of like CDN providers, Fastly, for example, that effectively are running on, I don't know if this is an old school term, but gold-plated hardware. So they have a beefy, really nice machine, and they do run in production thousands of WebAssembly components on their edge, which. Yeah, it's great cool. For being able to do that. Yeah, and that's why I do this, right? Is okay. Well, we can very efficiently bin pack basically our WebAssembly components on a single host, and scale them all the way down to 0. So that's what a little bit of this host config gives you some of that information, and effectively a host is going to be something that is in a pod, and all of this is wired together over NATs in the wasmCloud space. And I think we only have one more slide left, so let's do it so that we can get into code, because that's way more fun than tutorial mode. So, application manifest. I already mentioned that it's based on the open application model, and this is where you actually have your capability wired up. In the case that we're going to go through, it's very similar to this one that's on screen, which is basically giving it the ability to speak HTTP, which is something that you actually have to do for a WebAssembly component, because components themselves are in a sandbox. Part of that means they don't have access to networking unless you wire that up. You seem to sounded.
No, I was agreeing that, it's important to do HTTP or gRPC or, some flavor of networking there. Yeah. I think the next one is indeed a demo. Let's go ahead and go into that. And I believe in this one, we'll have the opportunity to look at one of those YAML files a little bit more. Okay. So we have been talking about Wasm. We've been talking about wasmCloud. One of the things that you heard about wasmCloud was that you can use it in any Kubernetes cluster, even your own. So in fact, we are going to do that. Broadly speaking, the way you get wasmCloud running in a Kubernetes cluster turns out to be you use Helm. I mean, I don't really know what more there is to say about it. This is, straightforward. We're installing the wasmCloud platform. We are doing it in the default namespace right now. We are explicitly feeding it the defaults from wasmCloud itself. And that's kind of all there is to it. And we're going to update dependencies for the chart while we're at it. Why not? There you go. Very profound. The next bit is not very entertaining to watch, but it is very important. This is the bit where we're saying perhaps we should wait for wasmCloud to be running before we do anything else. So now is your opportunity to ask questions or something along those lines. Otherwise, Bailey and I will have to figure out bad jokes to tell or something along those lines. Right?
Have a dance party. I don't know.
Yeah. Actually, nice. That took a lot less time than it normally does. So that tells me that quitting a bunch of things running on my Mac actually had a positive effect. These are also just kind of double checking that other bits of wasmCloud are working. Excellent. Everything is good to go. So the next thing we're going to do is we pretty much did the CRDs and the base controllers for wasmCloud, and we now have to tell it we actually want a wasmCloud host to be running, which we also do via Helm, using almost exactly the same Helm command that we did last time, except this one now has set host config.enabled equals true. Very profound. And the last time I tried this, it also took rather less time, which was nice. All right, there we go. So at this point, we have wasmCloud running, we have a wasmCloud host running, and we do have to do one weird thing, one weird trick. Later on, what we're going to do here is we're going to deploy a component that does HTTP on a particular port. That is port 8000. If you look carefully at the deployment for the wasmCloud host and the service for the wasmCloud host, you will find that it does not expose port 8000, even though we're going to need to use that. So we're just going to patch that in. I always feel a little bit weird showing patch YAML over here, but this is the critical bit, is we are going to add a port onto our 0th container. That one's going to be container port 8000. Its name will be HTTP. Its protocol will be TCP. But unfortunately, we also have to add a name to the existing port 0, because if we don't, then kubectl will scream at us because we have one with a name and one that doesn't have a name. And so it's yay kubectl. I mean, you could do this with kubectl edit as well, but it's a little bit more repeatable, at least for me, to use patch. Same thing with the service. This is pretty much the same information, except that the path looks different because it's just spec ports instead of spec templates container blah port, right? And also in this one, we have a port and a target port because we need to say you're going to expose port 8000 and you're going to direct that to port 8000 on your container. So now that we have done that and we just patched the deployment, we will wait again for the deployment to roll out, which it already did while I was blathering about the service. We can now make certain that we do see port 8000 listed in our wasmCloud service, wasmCloud host service, excuse me. I'm not going to bother showing the deployment because it's not very interesting, frankly. And finally, that lets us deploy the Rusty workload, which Bailey and I slaved over for, I don't know, at least half an hour or something, maybe.
One night, we made this really cool demo.
Yeah. And we will talk a little bit more later about why this is in Rust and not in Go. And I mean, sorry, other than the fact that Rust is the future of cloud native and it's what you should really be writing in, which I have, go see my talk in Paris about that. Other than that, we actually had a Go code base and we ended up doing this one in Rust instead. And we will talk about that later because it's an important thing to note right now. I wanted to call out a couple of things here, though. So you'll notice that there's this component that is using an image that gets pulled down from Buoyant's GHCR repo. This is the thing that we actually wrote, and that I actually compiled and pushed up into GHCR. So that component is the thing that's messing with code that I did. And it has absolutely nothing about HTTP in its source at all. This thing down here that says add a capability provider, which you'll notice is a different image. This is the bit with HTTP. So one of the things that's really interesting here is, first off, remember, I didn't have to write anything with HTTP. If you look even in the binary for the Rusty image that I pushed up, you will find nothing to do with HTTP. You'll find an interface definition that allows the HTTP server to talk to my component. And wasmCloud is going to take these things, cram the two of them together at runtime, and then do some magic to allow memory-to-memory communication instead of having to actually do IPC or anything like that over the interface between those two. Yeah, this was one of those bits that I found myself looking back fairly late in the game and going, hey, wait a minute. Because I am used to the model where, yeah, you import a library or whatever, but it links, it shows up in your binary, not a model where it's not present in the binary at all, and all of that happens at runtime later. As Bailey was mentioning earlier, this offers some deeply, deeply fascinating capabilities that we don't really explore in this demo in the interests of time, but would be a lot of fun to come back to in a few months and show off, I think. I think the rest of this is, it's, hey, look, it's a CRD. It's very exciting. And did you want to add anything there, Bailey, while this is applying?
No, I think if you've run with a custom resource definition before, if you've used Knative or OpenFAS or any of those kind of things, this probably doesn't look too surprising to you.
Linkerd or anything that uses Gateway API while we're at it.
Yeah, that too.
Yeah. So the important bit here is that we can look at this status and see that it has been deployed. Excellent. Well, wait. There we go. Excellent. In order to test this, we could test it with port forwarding. I hate port forwarding. So instead, I'm going to deploy a simple curl image into our cluster. And all this is happening in the default namespace again. So I'll make sure that's done. And then I'll use kubectl exec to curl to wasmcloud-host.default port 8000, which is the way I talk to my Rusty component. And I get an answer. Yay! I'm not really going to break down what exactly that answer looks like yet, but yeah. All right. The next thing we're going to do is we're going to come back over here for a moment, because the next thing we're going to do is we're going to use this as part of a larger application, namely the world famous Faces demo. Nobody ever acts impressed when I say that. Oh well.
Should I have clapped?
Faces is it's basically here just to demonstrate what a simple microservices app looks like. And I am going to, wow. Sorry, I'm dealing with my browser deciding to, or dealing with this stuff, deciding to just completely freak out. That's great. All right, let's see if it's gotten itself back again. Okay, that QR code takes us to the source code for Faces. Faces is back again. I feel much better. All right, Faces is a pretty simple application. It starts with a web browser and a cluster. The purpose of the web browser is to show the GUI for Faces. The web browser will talk to the Faces GUI, which talks to a workload called Face, which talks to another workload called Smiley, and to another workload called Color. Talks to Smiley with HTTP, talks to Color with gRPC. Smiley is supposed to return a grinning face. Color is supposed to return this blue color. The Face workload composites the two together and then hands them back so that that's what shows up on the browser. Right? This is the thing we're going to install right now. Back to our demo. None of this Helm install command is terribly interesting, except to note that by default, Faces misbehaves horribly, and we are going to turn that off. because this is not a demo about how to debug resiliency problems or bad applications. This is a demo about WebAssembly. So we will do that. We will make sure Faces is running. And then what should happen is that we see a running Faces demo. Very exciting, I know. This is also kind of not terribly interesting because what we're doing here is just running the plain old Faces demo with nothing to do with Wasm. So instead, we shall switch the Faces demo so that instead of talking to its original Smiley workload, it will talk to the Rusty workload that we just put up there. And when we do this, you should see things happen, interestingly, as the rollout happens.
I see crabs.
Yes, you should see crabs. This is good because Rusty returns crabs instead of the grinning faces because it's written in Rust. And yes, we deliberately set up Rusty so that it would obey the same API, the same interface that the Smiley workload would use, so we could just swap it in like that. That part is less Wasm-y magic and more just, basic programming. There's kind of no real point in checking the status on that rollout because we've already seen all the crabs. But hey, everything is great, right? Okay, next up. So far, none of this in the last 42 minutes has talked about Linkerd at all. So let's fix that. What is Linkerd? Probably people showing up to Buoyant Service Mesh Academy already have at least a passing acquaintance with Linkerd, but in case you don't, Linkerd is a service mesh. Whoops. I said Linkerd is a service mesh. That's what happens when you hit return in the wrong window. It is an infrastructure layer. The purpose of service meshes is to provide security, reliability, and observability at the platform level uniformly across the entire application, and you do it at the platform level so that you don't have to change the application. The reason behind all this one has to do with the transition from monoliths to the microservice architecture. A monolith, everything is self-contained. If you make a function call in a monolith, the function call might fail, but the act of calling the function will pretty much always work. You don't really have to worry so much about somebody coming in and snooping on the parameters to a function call from outside your process. Unfortunately, both of those things are absolutely possible in a microservices architecture because the network fundamentally is insecure and unreliable, and there is no way to change that with modern networking. It cannot be done. So instead, you use service meshes to make this situation better. Most service meshes out there, not all, but most, work by sticking a proxy next to every application pod and then allowing the proxy to take over all the networking communications, at which point the proxies get to do magic things. Unlike basically any other mesh, I used to be able to say any other mesh, but yeah. Unlike any other mesh, Linkerd uses a purpose-built, lightweight, ultra-fast Rust microproxy as opposed to using Envoy for its sidecars. I should point out there is a chunk of ambient that is written in Rust, of Istio ambient that is written in Rust. But it still
People
uses...
are catching on.
Yeah, people are catching on, right? Yeah. Ambient can only do layer 4 things with its Rust chunk of the code, and for anything, absolutely anything with layer 7, it still uses an Envoy. So just, something to be aware of. Everything that Linkerd does, all of the data plane stuff is in Rust because we want it to be fast. We want it to be secure. We don't want to have to worry about garbage collector slowdowns or random memory stomp CVEs. Rust is a great way to go for the data plane. And yeah, once the proxies take over all of the networking communication, they get to measure everything that's going on. They get to mediate communications. So for example, the proxies can enforce MTLS proxy to proxy. They can measure lots of things about what's going on, give you uniform statistics across your entire application, and you do not have to change your application at all. Also, the fact that the proxies sit next to the application means that your application can be written in absolutely anything. We don't care. And that is why, for example, sure, we can do this with the Faces code that's written in Go, where it's just a container running Go code, but we can also do it with the wasmCloud host, and then all of the Wasm stuff just works with Linkerd, and we don't have to think very hard about it, which is pretty cool. So the reason that you should probably care about all this stuff I've been talking about with the mesh is that security, reliability, and observability are not optional. I do not know of a single person who ever sits down to create a new application or a new product and goes, meh, it doesn't need to be reliable. They may say things like, reliability is not the immediate focus this week, but
it will
nobody, huh?
But it will be.
It will be, because the moment you roll it out and people start using it, suddenly reliability will become really important. Likewise, security, as soon as people are using it, security is a big deal. Observability is a huge deal as soon as you start having people complain about things going wrong. You can't operate without these things. And you have a couple of ways that you can do it. The first one is you can use a mesh. The second one is you can write a bunch of application code. And that's kind of it. Those are your two options. Obviously, I am biased, and I think you should use a mesh. But the flip side of that one is, if you look over this in practice, if you want to write it in application code, you are relying on all of your application programmers to get everything perfectly correctly written every time across all of your services in a way that they all can interoperate. And that is a very tall order in a lot of cases. If you use the mesh, you end up getting to let your application people focus on the business needs of the application. And you end up getting to let the Linkerd maintainers worry about all this other stuff. Kind of sucks for us, but it's a great trade-off for people using Linkerd. So what we're going to do next up is we will take Linkerd and we will stick it in everywhere here. And we will also do the same thing with our Rusty workload running in wasmCloud. It will also be brought into Linkerd. So let's get to it. The first thing we have to do when installing Linkerd is install the Gateway API CRDs that Linkerd relies on. And right after that, we will install the Linkerd CRDs that Linkerd relies on. These used to be one step, and over time, we as an industry have figured out that having everybody who uses Gateway API install shared CRDs like Gateway API can be problematic. So at the moment, Linkerd has made this a very explicit extra step. Actually, applying them isn't so much a problem. The problem comes if, say, you set up Linkerd and it installs Gateway API, and then you set up Argo and it installs Gateway API, and then you decide you want to go to Flux, so you delete Argo, and Argo deletes all the Gateway CRDs. That turns out to be a real problem. So that's why this is explicit. Manage the Gateway API CRDs separately. Do it on your own. Now we need to install the Linkerd control plane. Bailey, were you about to say something about that, or were you just sighing in sympathy?
Nope, that makes so much sense. And also, I feel like that layer keeps evolving, we started with ingresses or these endpoint slices. I'm talking about the Gateway API. I think, if you're just kind of casual about some of this, maybe some of that sounds surprising, but the way you explained it there makes perfect sense to me.
Yeah. It would be so nice if we'd had a really great service API in the beginning and we didn't need to do all this stuff. Unfortunately, that would have required 10 years ago to know how things would have shaped up over the next 10 years. So yeah, it is a hard problem. There's a lot going on there. And so we will try to keep explaining the good ways to do things. One critical thing that we need to do while we install the Linkerd control plane is wasmCloud uses Nats a lot internally, at least right now. Nats, I have a love-hate relationship with Nats. On the one hand, it can do some kind of cool thing. I'm not even talking about the whole CNCF recent drama with Nats. From a technical level,
not touching it.
Yeah, not just not going to do that. From a technical level, Nats can do some really cool things, that I really like that. But unfortunately, NATS is also a server speaks first protocol where the client connects to the server and then the server says something and then the client will send data. Server speaks first protocols are very, very difficult to manage at layer 7 because until the client says something about what it's trying to do, it's very hard for you to know what server to talk to if you've got multiple endpoints to choose from. So server speaks first protocols need special handling in pretty much all of the meshes right now. Actually, I think all of them, literally all of them. In Linkerde's case, we have a couple of different options. This one is the simplest. When we install Linkerd, we can say, hey, here are a bunch of ports that you should treat as just opaque TCP connections. And so we have listed the NATS ports that we are using at the end of this list. So when we install the control plane this way, any NATS traffic anywhere in the meshed application will just be treated as an opaque TCP connection and it'll work great. The rest of those ports are in there because if we set proxy.opaque ports when we install Linkerd, it overwrites Linkerd's normal default list. It does not add to it. So the rest of those are Linkerd's default opaque ports. I realize I said default twice and that probably sounded strange, but really it's the default set of default opaque ports and you can overwrite it later. And honestly, I'm kind of wondering if we just should add those ports in Linkerd. I'm not sure entirely why we leave them out right now. Once we install the control plane, we can install the Viz extension. We're going to use that to do some observability stuff so we can make sure that our Wasm component is really getting MTLS. The reason you're seeing something on your screen there about the install command is deprecated is because we're figuring out how to bring Linkerd Viz into the brave new world of the future. It's if you've used Viz a lot, you will realize that there's stuff missing from it, and we're trying to do something about that. So now we have Linkerd installed, we have Linkerd Viz installed. We will run Linkerd check to make sure that everything is happy. This is a good sign. I'm seeing a bunch of green check marks. It's sitting here at this point because it's going through and running some other extension checks that are silent. And this is one of those things that always takes just long enough for me to worry if it's frozen. So I'll just sit here and pretend I don't have to worry about that. You were going to say?
I think one thing worth calling out is probably the doc page where it goes through the opaque ports. I thought that was really helpful because it had this table where it was like, yo, if you're using NATS, make sure you do an opaque port here. So
I will.
You don't necessarily have to watch this video to get the good, but I think you including that full command on the default link is probably pretty helpful.
Yeah, it's not the first way I did it. The first way I did this was much more complex, and then I kind of was talking to some of the other folks at Buoyant about it, and one of them pointed out, I think you can just override that at install time, and life is so much better now. If you happen to have a link to the doc,
work on that. I'll work on that while you're driving. Yeah.
Okay, so now we have Linkerd going, and now there's a question about what is meshed at this particular moment, which we will use the Viz dashboard to answer. The Viz dashboard is a web page, which we will come over to here. Let's start off. If we look at the namespaces tab here, we can go through and see, oh, basically nothing interesting is meshed, right? Linkerd is meshed. Good. Linkerd Viz is meshed. Good. But the Faces application in the Faces namespace and wasmCloud in the default namespace, those are not meshed. So that's not terribly useful, really. So, thank you, Bailey. Bailey found the magic page. I'm just going to go ahead and take a second to put that up here. Opaque ports documentation. This is the thing that we were just talking about. That does have a table that talks a lot about what's going on, and the command that you'll see earlier in this presentation, or that you can find by looking at the GitHub repo, is sort of the end result of all of that. So since nothing is meshed right now, and we would like things to be in the mesh so we can do Linkerd things with them, we're going to start by putting faces in the mesh. This is pretty simple. We annotate the faces namespace with linkerd.io/inject equals enabled, and then we restart the workloads in the namespace. And while we're at it, we reload the web browser because it got confused. In theory, we're not going to see anything different come up here. We might see a couple of random things happen like this because I'm only running one replica of things. But there we go. We're back again. All good. If I'd started multiple replicas of these workloads, we probably wouldn't have seen that. And if we look at the Viz dashboard now, then we will see that all of the workloads and faces are meshed. We can click through the faces here. We see a bunch of good stuff. We can see metrics like request rate, success rate. We get to see latency, all of this great stuff that happens the moment we put things in the mesh. So that's kind of nice. We also, a fairly recent thing that showed up is the Linkerd viz stat outbound command. This command is saying, hey, Linkerd viz, tell me what you know about outbound connections from the face deployment in the faces namespace. And if I run that, we can see, oh yeah, it's talking to color and it's talking to wasmCloud host, and it gives us port numbers and successes and things like that. So Linkerd already knows that we're talking to our Rusty workload in wasmCloud. This view doesn't actually tell us anything about whether that connection is meshed. We know it's not. You still get information about it because the proxy in the face workload gets to capture information about that outbound request. But if we want to prove to ourselves, or maybe to the auditors, that it is not meshed, we can come over here into Linkerd viz. If I click on the face deployment and then scroll down to the bottom, you see this bit to default wasmCloud host with the scary warning on it. That's the
doesn't have an identity.
Yeah. And now it just went away because of Viz being Viz. Eventually consistent, man. Gotta love it. But also, if I click on this deploy wasmCloud host, it screams at us that this is not meshed. And it won't tell us anything terribly interesting about it because it doesn't know. So we should fix that. We end up meshing wasmCloud exactly the same way that we meshed the Faces application. In fact, we'll mark the default namespace for injection and then roll out all the deployments with stateful sets. As it happens, we are definitely going to see interruption here because, again, there's only one replica, but also because if you look at what's going on, you'll realize that the NATS stateful set pods have to get rolled and they take a while to come back up. So that's what's going on. This is not, you can't really say this is wasmCloud's fault. I'm pretty sure you can go and run this in a way where it won't be badly affected like that. I'm sure Bailey can speak more to that though.
It makes more of a fun demo this way. I mean, we could have distributed it to multiple wasmCloud hosts, but we opted not to. You know, we're keeping it simple for the demo.
Dirt simple. Yeah. Yep. Still waiting for NATS and all that too.
I did appreciate the emoji that you used for that when it went down. That was pretty good. Top notch.
It's you know, I'm not going to tell you how long I spent when I first wrote Faces. I'm not going to tell you how long I spent with other ideas before going, wow, I'm being an idiot. The Unicode people spent a lot of effort designing these faces. I should just use them. And I'm also not going to tell you how much time I spent looking at various different faces for the different error conditions before settling on, you know, the screaming face and the vomiting face and things like that. Because I am an engineering professional and I would never, you know, waste time on such things. But you can see now that the wasmCloud host deployment shows up as meshed, which is great. And if I go back to the faces namespace, oh, wait, actually, if I come back to this, we can see default is meshed. Excellent. And we can see all these things. It even meshed the curl pod. Very nice. If I go to faces and then I click through to the face deployment, I now see stats and such for deploy. And if I come down to edges, I see a green check mark for my connection to wasmCloud. So this lets us be much more confident in the idea that, yes, it really is meshed. MTLS is happening. All the goodness is going on. So one other fun thing that we can do here, since this is meshed, we get to use things like Gateway API CRDs to do dynamic routing, because from Linkerd's perspective, this is just an HTTP connection from one meshed workload to another meshed workload. And the fact that one of them happens to be written in Rust, compiled down to Wasm, is totally irrelevant. So I can do things like use this, where if you look over at our application, these 4 cells in the middle, if you can see my mouse, these 4 cells in the middle, when the face workload calls back to Smiley and, well, Rusty and color, then it uses a path that contains /center. And for all the other ones, it has a path that contains /edge. So we get to tell the difference between those groups of things. We also have a row number and a cell number, or a column number, and we could do really fancy things. But for right now, we're just going to work on the center and the edge. And what this HTTP route says is, the name is the Rusty route. We're going to put it in the default namespace. This is important. When you are doing routing with Gateway API, in almost every case, you have to put the route in the same namespace as the originator of the request. If you put the route in the namespace that receives the request, you are doing something different, and it's not going to work the way you think it will. Bear that in mind.
Sounds like from experience.
You would not believe how much debate went into that in the Gateway API working group. Oh my God. Yeah, it's... the problem is that if you do it in any other way, you are introducing a nasty potential for circular routing, and very, very bad things can happen. So yeah, generally speaking, you got to put the route next to the originator. Also, generally speaking, one routing decision gets made. You can't have an HTTP route stacked on top of another HTTP route. We're going to bind this so that this route will affect any request made to the wasmCloud host service on port 8000. So that's going to be the requests from the face workload going over to the host. I just realized I said that totally wrong. You want it to be next to the thing receiving it in the same cluster. Never mind. I cannot talk.
We've been going for over an hour now. It gets harder and harder at this point.
It kind of does. So everything that I said about making sure you get the namespace right, still true. Excellent. Top marks. But no, it needs to go next to the thing that is receiving it. Okay. The rules here, anything where the path starts with /center is going to get routed to the workload named Smiley in the faces namespace. Anything that doesn't match that is going to continue on to wasmCloud host on port 8000. This may seem like you would have an infinite loop of things going to wasmCloud host, then getting sent back to wasmCloud host. I will defer you to documentation on the Gateway API page, because that is going to take a little while. But you can go take a look there and read a little bit more about that. The short version, though, is that it'll be fine. Trust me. And when we apply this immediately, we will see smiley faces in the middle and crabs all around the edges. grinning faces in the middle even, and crabs all around the edge, because Linkerd is now taking that traffic that would otherwise go from face to the Rusty workload, notice the path, and direct it instead to the original smiley workload, so we get smiley faces. And with that, I believe that we are finished with the demo.
Mic drop. Okay, it just all worked. I love your emoji for the, like, hey, we're doing a live demo here, so fingers crossed. Not so bad.
Yeah. I mean, demos, it's always nice when the demo works. Really, it is. Gotchas. We like to talk about gotchas in Service Mesh Academy because this is real technology as opposed to ideal technology. And there's pretty much always some gotchas. And there are a couple of interesting ones here for sure. The big one, if you're working with Linkerd and wasmCloud, is that you must mark the NATS port as opaque. The good news is if you forget this, it is not a subtle failure. Just nothing works. wasmCloud refuses to come up. It is immediately obvious that something is wrong. So that's the good part. You don't get weird, subtle things. You get big, immediate, horrible things. Another big one is right now, all of the Wasm components in a single instance of the wasmCloud host will share an identity from Linkerd's point of view. And, yeah, this is a thing that we are hunting for a way to do better with. So,
yeah, think about it this way. We have a single process that has a single IP running in potentially thousands of different applications and components. So what we did for this demo is kind of the functional equivalent of a lift and shift. We've got it working here, but it's not yet taking advantage of all the different things that we want to take advantage of.
Yeah. Now, that being said, there are probably a lot of situations in which you can have a wasmCloud host with a huge stack of Wasm components that are all doing a single job where it makes sense to have that host have a single identity. And you can spin up multiple hosts too. So it's not the end of the world, but having a better solution is something that would be really, really nice. Another gotcha. I said we were going to talk about this earlier. What I originally did with the Rusty service was I took the smiley workload in faces, which is written in Go, and I said, this is going to be awesome. I'll just go through and compile it to use the Wasm stuff, and that's all I have to do. That did not work. The reason it didn't work is that the WasmB2 stuff that Bailey was talking about earlier is not yet part of the Go standard library. And all of Go's networking stuff is in the standard library. So in particular, I was trying to use NetHTTP in a couple of places, as one does when writing Go, and that turns out to be a problem. I don't know if there's a simple reason for why it's a problem or anything like that, but the end result was that Bailey at one point said, suppose we just do a really simple version of this in Rust. And I said, yes, let's do that. I mean, I kind of would like to port all of Faces over to Rust, so it's not exactly a sidetrack sort of thing, right? And oh my God, so much simpler. We pretty much did that and compiled it, and it just started running. It was great.
Yeah, if you're doing a greenfield application and you're bringing in your dependencies and you've got one place where you're doing NetHTTP, it's pretty easy to use the wasmCloud's Go SDK to swap in to WASI-HTTP. But Flynn had a really wonderful abstraction that he built, and that was not the case for what he had. And it's definitely cool. We're definitely working on this.
Yeah, if you look at the code for Faces, the abstraction is there because color speaks gRPC and smiley speak HTTP, but they share most of their code because they're fundamentally doing most of the same job. So there's an entire abstracted HTTP layer in versus gRPC, and great software engineering practice, if I say so myself, did not go well trying to do this with TinyWasm. So bear that in mind. Yeah. And finally, I think you were going to talk about this one as well, Bailey.
Yeah, I think it's really important to know that your WebAssembly code is sandboxed, which means you need to give it those capabilities. So there, you might run into things that you can't just do. You could do it in a container, but you can't do it in Wasm. Today that would be spawning threads. Spawning threads is something that the runtime really wants to control, and you can't do that. That would break the sandbox. There are some other aspects here that do require an interface. Like if you want to access a GPU, there's an interface for you. It's called WASI GPU, and that could work really well. But it does mean that the code that you're compiling needs to be speaking over basically these interfaces so that the host runtime can wire you up to have those right capabilities because you are sandbox. So I think that's an important thing to know. Ultimately, the goal where we are heading is that I don't really want anybody to have to worry about taking their code and compiling it to WASM, but that's not exactly the world we live in today, and so it's a good gotcha to call out.
Just out of curiosity, how does WASM deal with, what mechanisms does WASM have, or maybe I should say, does WASM time have if you want to do concurrency?
Well, when you're running WASM workloads, really you would want to lean into a different paradigm here where you would spin up thousands of instances, whereas previously you might create a thread pool and do that yourself in your app. With WebAssembly, because instantiation is practically instant. Instead, you just you make 1,000 functions, and then they all handle that and bursty, and then go all the way back down to 0. That's by far the best way to handle this type of kind of in a way that's concurrency type problem. Now, there are other things that we've been working on. So we talked a lot about WASI P2. That's effectively what this demo is built on top of today. We're also working on a future version of this spec called WASI P3. WASI P3 supports structured concurrency and native async in your components. So what that basically means is that it's a lot easier for you to bind and create language bindings that, if you're using async await, and let's say in your REST code, it's really easy to take advantage of that. The runtime is really smart about how to efficiently switch your stack. You're able to do async. Obviously, we're making HTTP calls in our component today, but by giving this power to the WebAssembly runtime, aka WASM time in this case, we can do this very efficiently at scale. And we can give a really good experience for the tools that compile to your .wasm.
And I'm sure that was all really easy to implement.
Yeah, we actually solved the function coloring problem. If you're familiar with that in computer science, Luke Wagner, he's one of the creators of WebAssembly. He's the champion of the component model, and what he effectively built is a way. When we say function coloring, what we really mean is, in a lot of languages, you have the function coloring problem, which is like once I turn something async, now everything has to be async, like everything that I call. And
it's a
with
problem.
this, that's not the case. That's not the case with WebAssembly components. You can go async to sync and sync to async, and it's great. So that's with the next version. It's not out yet.
The expression on my face is kind of like, I'm gonna have to go look at that. That sounds too good to be true.
Yeah, he talks about it in depth at wasm.io about a year ago. So Luke Wagner. He has this silly name, but that's so good for the title of the talk. It's like, stream something. He did it with his syntax of his talk. Hang on, I gotta get you that link because I think that's a really cool one to talk about. That goes in deep.
That would be a good one to put up there. While Bailey is doing that, we running Service Mesh Academy would love some feedback. Scan the QR code there. Tell us what you think. Tell us what you like and what you don't like, and we promise we'll take it seriously. It's important to us. We want these to be better. We want them to be good for people as opposed to not so good for people. I just pasted in the workshops channel the Wow, that is a terrible, terrible title. Oh my god.
It's not one I can easily say out loud, but a
I
stream
was just
of consciousness on the
realizing,
future async of the component model.
let's just do it this way really quickly. There you go. There's the lower third. Wow, what a terrible, terrible appropriate name. Wow.
It tells you what you're in for.
Yeah,
Like, all right,
it
let's
really,
talk about
really
some
does,
computer
doesn't it?
science stuff right now.
Yeah. We do have a couple of questions that we'll come into in a second. Shameless plug, you should go try out Voyant Enterprise for Linkerd. It's what we were using today. It pretty much works. And we have certification courses as well, which you should also go check out because they're pretty cool. And in a month, just shy of a month, I will be talking about anti-complex multi-cluster using federated services, which, okay, I realize that I'm biased and this is just a horribly geekish thing to say, but federated services are incredibly cool because they act like services and they span multiple clusters and they just work, and it's kind of amazing. Question from the Linkerd Slack. I feel like I should just paste this so everybody can see it, but I guess I'll read it instead. I've tried to play around with Rust and Wasm a few times so far, and it always felt like language support is lagging behind new spec versions popping up. The question, is WASI narrowing down to an actual standard? Or is my impression wrong?
Let's see. I held that vote last year, January 2024. That was basically, the starting signal for languages to actually start bringing it into their standard language libraries. Yash Watts, who's an engineer at Microsoft, helped get a lot of this into Rust proper with WASI P2. So now, yes, you can say cargo build dash target wasm 32 WASI P2, and
which we did.
You're not, which is exactly what we did.
Which we did, and it worked. It was great.
It's getting pretty good. Probably what the engineer you're talking to tried to do is build with, let's say, request, one of their favorite libraries in HTTP. We do have a PR up to add in WASI PT for that, but effectively what everybody was waiting on is, okay, standard language library tells me how to compile to this thing, and then every dependency along that chain starts doing that change, and then you start getting to the higher level library. Well, I say library, but I should be saying crates in this world. But crates in this situation, like request, to support WASI P2 natively. I'm really hopeful that a lot of those will start landing. In terms of getting close to a standard, I would say that we are. The last major set of talks that we've done over the past 6 months was really about what our road to 1.0 looks like for WASI. When I say WASI P2, really just think of semantic versioning. We're major version 0.2. And we've been making incremental patch updates over the past year, mostly doc fixes, but some deprecations, some cases where the API wasn't quite right. We made some tweaks, which we were able to do because we have versioned interfaces. And, standards are pretty slow. So I think, is it going to be a standard this year? No. Could it be a standard next year? Maybe. But probably another year on top of that. But that does not mean it's unstable. It's now that it's in, WASI P2 has many years of support, and it is stable. And people can build and take advantage of it today. And WASI P3, what I was talking about, there's going to be a really simple migration path. Most of the runtime set support WASI today will be able to seamlessly virtualize WASI P2, aka they only have to really support WASI P3 to support their WASI P2 counterpart. So the upgrade should be seamless. I'm helping lead out a lot of that work. So you can.
So you're in a good position to influence that. Yeah, exactly. I think that's going to be the poll quote for this interview. Standards are slow.
Standards are slow, and you need them. If you're trying to make a change that shows up in standard language libraries across the entire industry,
anything, really.
Yeah, you got to have a standard.
I mean, one of the common complaints with people is that gateway API is gateway API moving slowly. It's exactly the same thing. It's moving slowly because we have to be careful to try to not break dozens of implementations used by who knows how many people. So yeah, it's difficult.
For us, it's solving how does every language do async and making them all work seamlessly together.
It's okay. You can just tell all the languages the right way to do async, and I'm sure they'll just
Obviously,
all
yeah.
fall
They'll
into
just
line.
change, right?
Yeah,
That
that's
just
the way
works
that
great
works.
telling
Yeah,
Go
that's
what to do.
yeah, that's the way that works, right? You just kind of go, yeah, no problem.
No. Yeah.
Yeah, I mean, I'm sure telling the C folks works even better than telling the Go folks too, right?
Yeah, so I would say anybody that wants to get started, the easiest way to do that, instead of trying to do something where you're taking brownfield, picking an existing app that you've been moving forward, I recommend starting greenfield. Use what we did in this case that got something done in less than an hour,
An hour.
basically. We ran wash new, so we ran the wasmCloud shell that's from wasmCloud, and we created from a Rust template. And inside that Rust template, it relies on a component SDK that's written in Rust, and that gives you the right way to do HTTP and a lot of other things, and kind of makes it a lot easier, puts you on a happy path. So that's definitely my recommendation for people getting started.
I can actually show a little bit of that. So this is the source. It's almost entirely a single Rust file. That's the whole source, actually, all 217 lines of it. And if I run wash dev, then it will go through and build this and tell me it's deployed. I don't know what this is. What is this?
That's basically a Nats thing. Ignore it for now.
Yeah. Awesome. So if I get another tab here and I curl to localhost 8000, then there you go. I've just talked to my thing. And yeah.
Show how small it is. Do an lsltr in the build directory. Because I talked about how small they are. Are they actually small?
328 kilobytes.
That's pretty small.
Pretty small. What's the difference between rusty.wasm and rustys.wasm?
Yeah, we sign it. So that way we're able to, kind of test who built it, where, what tools, and all of that information. WebAssembly binary has this section called custom metadata. And so we've added some of that information in the custom metadata. But if every byte matters to you, you don't have to use the signed version.
I haven't done this before. I'm just kind of curious.
Yeah, I think you have Wasm tools installed if you want to look at some WAT, or as we should probably just go ahead and change the name. Yeah, so say Wasm tools print, and then give it that Wasm. So
I'll use the signed version just for the fun of it.
Yeah, hit enter, see what happens.
Whee. Oh my god.
So there's that sign that you saw that right at the end, and there's that first set of bytes saying it's a WebAssembly component, and now you can see all those interfaces. Yeah, so important to highlight, the WebAssembly component basically is giving you kind of metadata for how these interfaces work. Now if you go several pages down from here, right now we're seeing things say strings, but now we're starting to get into the good stuff. So core WebAssembly, the standard. Oh god,
it's mangled function names.
It's so great. It's actually I32s as far as the eye can see. It's numbers. It's pure compute. That's literally what we're talking about when we're talking about what is a WASM module. Pure compute in a sandbox. And we had this problem where lots of languages were compiling to WebAssembly, but they didn't know how to talk to each other. And that's what component model solves. That's what interface type solves. Yep, you do have mangled function names, but I think that's because we didn't do a release build here as part of it. That's okay. We could get smaller. That's what that means. But also...
All right, well, let's just go ahead and try that. Sorry, also what?
Well, we could go that way, but actually, do you mind? Let's show them something prettier because we're looking at binary. Like we're looking at the guts here. Let's do Wasm tools component wit, and actually, there's a shorthand for this. If you're using wash, you can say wash inspect and give it the binary as well. But same wash embeds Wasm tools here. So Wasm tools component wit and give it that build rusty.wasm. Boom. Okay, so what you're looking at now, prettier. It's way better, right? Okay, so the root, that is when the WebAssembly runtime loads this thing up, it's like, what do you need? And it says, oh, I need a bunch of WASI stuff. Like, I need the standards. Give me these standard spec things. Almost all of that is fulfilled by the WebAssembly runtime that we're using, Wasm time. And then it's saying, yo, you can call me. I export this API. This is my API. Call this, aka, you're sending a request in, and it's taking that in and coming and giving you an HTTP response back. That's how it works. That's the. We just went deep in a 101, Flynn. I don't know if we were supposed to do that, but
sometimes we get not to. Sometimes we get 101s wrong. I mean, what are we gonna say here, right?
Well, but hey, it's not magic. It's actually all declarative. It's.
I'm also
well defined.
Whoops! It'd help if I kind of got that back in the correct order, right? Okay, so there is some magic there for turning this function handle into that incoming handler thing, but that's okay.
Yeah, that's coming from our component SDK, and basically it's just saying you're using this, and so we're going to export that interface when you compile this code.
Cool. I don't see any other questions. We are pretty much at time. We managed to burn an entire hour and a half on a 101 with a demo. That shocks me not at all.
It was fun.
So thanks everybody for coming. Really appreciate it. We will see, or I at least will see y'all again in July. Go and check out Cosmonic's work. Did we do a Cosmonic lower third? Well,
no, we don't have to. I'm going to make some splashy stuff.
Actually,
so hold off.
Okay, I was going to say we did do this one at least.
Yeah, let's talk about.
You can go check out. You can go check out wasmCloud.com. You saw it working. It's pretty cool. We like it. And yeah, off we go. Thanks much, Bailey. Appreciate it.